My name is Alphonsus Adu-Bredu. I present here today our work on optimal constraint task planning as mixed integer programming. This work is in collaboration with Nikhil Devraj and Odest Chadwick Jenkins. Imagine you woke up one morning and go to your kitchen for breakfast, only to find it messy from last night's cooking. Also imagine that you have a robot butler who is in charge of cleaning chores in the house. You ask the robot butler to clean up the kitchen. Upon receiving the command, the robot decides to generate a plan to accomplish the task, which involves stowing away the sugar canister to the shelf. The canister's pose can be estimated using an approach like clear pose, which was proposed by Xiaotong Chen et al. The first question the robot asks itself is, what actions should I take to shelve the sugar canister while expending the least amount of effort? Another question the robot asks itself is, what should my stance pose and grasp pose be in order to pick the sugar canister and place it on the shelf? The question the robot is really asking, and one which this work aims to address, is, how do we plan the optimal sequence of actions that satisfy all numerical constraints? To address this question, we propose GTP-MIP as an approach for optimal constraint task planning. Given a task with symbolic and continuous goals and constraints, GTP-MIP outputs a grounded plan made up of logically consistent actions with optimal continuous parameter values. The robot can then execute these actions to accomplish the task at hand. How does GTP-MIP work? Given a description of a task planning problem with an objective function and geometric constraints, which we call the optimal constraint task planning problem, GTP-MIP first builds a hybrid funnel graph, which is a planning graph with alternating layers of states and action levels. The hybrid funnel graph and a task description are then encoded as a single mixed integer convex program with discrete actions as integer variables and continuous action parameters as real-valued variables. The mixed integer convex program is solved to output a grounded task plan made up of a sequence of actions, each associated with optimal parameters. The grounded task plan is then executed by the robot to accomplish the given task. We evaluate GTP-MIP on a simulated warehouse rearrangement problem, where the robot is tasked to rearrange boxes to satisfy specific geometric task constraints. The geometric task constraints for this particular experiment are listed in the table below. GTP-MIP is able to generate an optimal task plan with optimal parameterized actions that satisfy all the geometric task constraints. We also evaluate GTP-MIP on a real-world shelf-stocking task with a physical robot. The geometric constraints in this task are robot stance constraints and grasp constraints. GTP MIP is able to generate optimal actions that are successfully executed by the robot. By accounting for geometric task constraints in task planning, GTP MIP takes us a significant step forward towards realizing the dream of robot butlers capable of stowing objects on shelves and cleaning our kitchens. A drawback of our system is that the low-level controllers are not reactive controllers. As such, when the robot misses a grasp due to inaccurate object pose estimation, we often have to manually reposition the objects, which is obvious in the cuts in this demonstration video. Using reactive low-level controllers, as well as robust object pose estimation, will be a significant step towards making our approach reliable and deployable on real-world service robots. Thank you very much.